I have the pleasure to introduce Professor Hugues de Riedmatten today. He's one of the main authorities in experimental quantum information, and in particular in atomic ensemble quantum memories. I have the personal pleasure of knowing Hugues since a long time when I was also working in ICFO. And Hugues, to say something about him, I mean, it's a very short summary. It's difficult to say all the things that he's done. He got a PhD from the University in Geneva back in 2003 in Switzerland, after which he did a postdoc in Caltech. Then he came back to Geneva as a senior scientist, and in 2010 he got a permanent position as a principal investigator of the quantum photonics group in the Institute of Photonic Sciences in Barcelona, right? And he's also a professor at the Catalan Institution for Research and Advanced Studies, ICREA. Like I said, his work focuses on experimental quantum information, quantum optics, quantum memories for light, quantum light sources, quantum frequency conversion, and quantum nonlinear optics. He's also been awarded many research grants, including grants of the European Research Council. So it's really a pleasure to have him here and listen to such fantastic developments that his group has been doing over the last over the last few years, right? So thank you so much again, Hugues, for being here. And oh, by the way, for all those who want to ask questions during the talks, Hugues is fine with that, so you can simply raise your hand and I will interrupt him to let you ask the question, right? But we can all, I will let you all, I will give you the right to speak, all of you, I will free you, okay? So Hugues, please proceed. Thank you.
Well, thanks a lot, Leandro, for the nice introduction, and also for the invitation. It's a real pleasure to be able to speak here for this brand new institute. So I'm going to talk today about the work that we are doing to develop quantum repeaters in quantum networks. And you can see here some of the pictures that I will show. Let me just that I will describe during my talk. Before we start, let me just tell you where I am from. Leandro knows this place very well, but maybe not everybody knows. So we are the Institute of Photonic Sciences in Barcelona. So this is Barcelona, and we are maybe 20 kilometers south of Barcelona. And in this institute, we are dealing with all the science of light, going from nanophotonics to nonlinear photonics, to biophotonics, and finally quantum optics. And my group is the quantum photonics group, as Leandro mentioned. And what we are doing is really trying to develop the quantum technology for quantum network. So what is a quantum network? So the dream vision that we would like to have in the far future is to be able to distribute entanglement over ideally global distances. But for now, let's focus more to, let's say, continental distances. So a quantum network would look something like this, where you would have
We have some audio interruption. Hugues, could you repeat the last 30 seconds? Sorry, we had some audio thing. Okay. I think.
Yeah, so I was saying that we want to build quantum information network. Can you hear me now well? And so basically what we would like to do is to distribute entanglements over very large distances. And for this, we want to build quantum network, and the quantum network is composed of quantum nodes, which are material system, which we can use to store and process quantum information. And we have quantum channel that links this system to distribute now entanglement, for example, using photons, for example, using optical fibers between these nodes. And there are many applications that we can imagine if we can do such a thing. Of course, there is the very well-known network secure communication using quantum cryptography. But in the future, we might also imagine linking different quantum computers together to increase the Hilbert space associated to this quantum computer. Or we could imagine having doing secure cloud quantum computing, light quantum computing in the cloud. and also some other applications, for example, to increase the resolution of telescopes or of clocks. So ideally, we would like to distribute an entanglement between all of the system, but if these nodes are too far away, then we cannot directly use send photons into an optical fiber. The photon will be absorbed after a few hundred kilometers. You have this exponential absorption in the fiber, and so this becomes highly unpractical. So the idea, if we want now to distribute entanglement over distances much longer than the fiber attenuation, is to build what we call a quantum repeater. The quantum repeater is something like this, where you have quantum repeater links, where you distribute, let's say, the total distance into several links. And I show here 2 links to start with, but we could in principle have more links. And then the idea is that we want to distribute entanglement within one link, to store this entanglement in quantum memories, and then once the 2 links in that case are entangled, we want to make some sort of Bell measurements between those 2 links to extend now the entanglement over longer distances. And again, here there are two links, but in principle, you could imagine to have more links if you have good enough, let's say, quantum memory. So this requires heralded creation of entanglement. You want to know when you create your entanglement, and you want to be able to store this entanglement in quantum memories. Okay, so in the rest of this talk, I will talk about what kind of quantum repeater nodes we have in mind. And then I will talk about 2 different experiments. One is a recent experiment we have done where we did created entanglement between multiplexed solid-state memories. And then later in the talk, I will talk about our current efforts to go towards integrated quantum memories to try to really get a fiber integrated quantum memory. Okay, what do we need if we want to make a quantum node for a quantum repeater? So first thing you need is that you need to have an interface between your photon, ideally a telecom photon, and microqubit. So we would like to have entanglement between telecom photon and microqubit. Then you want to that this qubit lives for very long in the quantum memory. You would like to have long storage lifetime in the quantum memory. And ideally, you would also like to be able to have not only one qubit, but many qubits stored in this quantum memory. So you would like to have what we call a multiplexed quantum memory. This would be very important as we will see. And finally, also something that would be nice is to be able to do a quantum logic between the qubits which are in this quantum memory. So there have been many platforms that have been proposed. I show here a few. This is not an exhaustive list. For example, cold and hot atomic gases, rare earth crystals, single trapped atoms or ions, or color centers in diamond. So today I will focus on this one, on the rare earth crystals. So these crystals are actually here on the periodic table, and they are a very nice system for this kind of applications because they give a very large number of stationary atoms with optical and spin transition. So you have optical transition where you can, in principle, absorb the photon, and you have spin transition for doing long-term storage of these photons. Yeah, so the nice point is that the atoms are naturally trapped. You don't need anything special to trap them. And also, if you cool them at very low temperature, typically below 4 Kelvin, you have very good coherence properties. So you can, in principle, these transitions are very narrow transitions, and you can have very long coherence times. Another interesting property is that you have inhomogeneous broadening, but unlike with, for example, warm atoms, this inhomogeneous broadening is static. This means this is because each ion in the crystals is slightly different crystal environment, and so you end up with a static inhomogeneous broadening. Usually, this is considered as a draw. We can use it basically as a resource for doing multiplexing in time and in frequency, as we will see later. And finally, something which is again also very interesting is that since this is a solid state, it's compatible with integrated design. So we can do waveguides in these systems, and we're able to create integrated design with these systems that we will also see later. Okay, let's see now how we can create now entanglements between these two different crystals, for example, two different memories that are far away in principle. So this is one way. It's not the only way, but it's the way that we will use. So imagine now that at each location you have a source of photon pair which creates two modes, A and A prime, and you will store this mode A in the quantum memory, and the mode A prime you will send it into an optical fiber, and you do the same here at B. You have two modes, and now you will basically pump these two sources. So these are, for example, spontaneous parametric down conversion sources. You will pump them, and you will generate now a state where you have a photon pair created here in coherent superposition with a photon pair created there. If you combine these two modes A prime and B prime at the beam splitter at a central location, and you have a click, you have detection, a photon detection that we call click. What you will have, the conditional state that you will have, is that you will have basically this beam splitter will erase information about the origin of the photon, so you don't know if the photon comes from source A or from source B, and you will end up with a state where you have one excitation stored in the memory A and 0 in B, and the other way around. And so we have this 1 0 plus 0 1 state, and this is actually an entangled state, and it's heralded now because it's heralded by this click that we have at the center. It's heralded in this, it's entangled in what we call the FOC basis, in the sense that we have one excitation in one memory and 0 in the other one, and the other way around. And we can see here something important already, that there is this phase EI phi here, which will be given by the phase acquired by this mode A prime and B prime from the source to the beam splitter at the center. We will come back to this when we talk about the experiment. So this scheme is actually very similar to the famous DLCZ scheme by Duan, Lukin, Serac, and Zoller, which was proposed in 2001. But it has two advantages over this, I would say. One is that you can optimize now the wavelengths. So for example, these wavelengths of A and A prime don't need to be the same. This means that A would be resonant with your quantum memory, and for example, A prime could be directly a telecom wavelength. And we will use this feature to really make now entanglement between the photon and the quantum memory. And the second one that we will also see, that you can now use this memory as multiplexed memories, multimode memories, and this will allow us to boost the rate of entanglement. So how does it work? This is something actually important to get practical quantum repeaters working. So I want to spend a bit of time to explain how it works. So we have again our experiment, and if you have a conventional memory that can store a single mode or single qubit, you would have to wait a long time between two trials. And the reason is that it's important, as I said before, to have heralded entanglement. So you want to emit your photon from the source, the photon to travel all the way in the fiber down to the Bell state measurement, and then the information has to come back to the memory before you can try again. And so if you have now a long distance between these two nodes, this will actually limit a lot the repetition rate of your experiment. So for example, if you have 100 kilometers, the time that it takes, so that we call the communication time, for the photon to arrive from the source to the beam splitter and coming back, is in that case 500 microseconds. So this will limit your repetition rate of your experiments to 2 kilohertz. And then you also have loss, for example, in the fiber to go to the central station. And if you use probabilistic sources, the probability to generate the entanglement is also very low. And so in the end, you end up with a very, very small success probability per trial, and you cannot repeat many often the trial. So you will have a very low entanglement rate. But now, if you can imagine that you can store many modes in the memory, for example, temporal modes, or it could also be spectral modes or spatial modes, then you can try many times during the communication time. And this means that your repetition rate now will be increased by a factor of more or less n, where n is the number of modes that you can store. And in principle, you can store something like 1,000 modes, bigger than 1,000 modes. It has not been done yet, but it could be done in principle. So you have a very nice speed up of your entanglement rates in your quantum repeater. So for this, if you want to make such an experiment, what do you need? You need first that the storage time in the quantum memory is at least L0 over C, at least the communication time, such that when you have a click at the center, you are sure that your entanglement is still present in the two nodes. And then you need to have a photon pair compatible with a memory and with a fiber network. And you need to store in the memory and distinguishable mode. You need to be able to distinguish these modes and to selectively read them out to make sure that you can combine them adequately when you do the band state measurement. Okay, so let's move now to see a little bit more what is our quantum node. Actually, we have seen how to try to build a quantum repeater link. Let's see how is our node. So we use, as I said before, a rare earth doped crystal. In our case, we use a praseodymium doped crystal, which has more or less this level structure. This is the relevant level structure. You have 3 hyperfine ground states and 3 hyperfine excited states, and an optical transition at 606 nanometer. And typically, the coherence time, the spin T2 of the spin state, is something around 1 second. And the optical transition coherence time is around 150 microsecond, which is actually very long for such a solid state system. So the reason we like this particular material is that it has a structure which is suitable for doing what we call spin wave storage, meaning that we want to store quantum information as a superposition of these spin states. And you can have, in principle, long coherence time. So people have demonstrated that you can store at least classical light for up to 1 minute with these crystals. And it's not easy to do the same with single photons, but this would be our long-term goal to do that with single photons. People have shown that you can store light efficiently also in these crystals, up to 70% storage and retrieval efficiency. So they have very nice storage properties. They have one drawback, though, that the bandwidth is rather limited because the splitting between the states is quite small. So you have to see here 4.6 megahertz between the two states, which means that the bandwidth is something below 4 megahertz. So this means that also that we need a source which is able to create this the states below 4 megahertz, and this is not so easy. But before that, let's quickly tell you how we want to now to store quantum information in this kind of system. What we will use is the so-called atomic frequency COM scheme, and the idea is the following. So let's start by a 2-level system, which is inhomogeneously broadened. So this thick line here is because it's inhomogeneously broadened. So now if you arrive with a photon and you absorb this photon in this line, you will generate a collective excitation. So you will, the photon will be collectively absorbed by all the atoms, and you will create a state where you have all the atoms in G except one in the state E. But this state is shared among all the atoms in the crystal. So you have this collective superposition. But now if you do nothing, this collective superposition will quickly dephase and you will basically lose your photon. But now if you are able to shape your absorption profile into a series of very narrow and absorbing peaks that we call an atomic frequency COM, you would have a natural rephasing that will occur. So the photon is absorbed, and then all the dipoles will start to dephase. But at some point, which is equal to at some time, which is equal to 1/delta, where delta is the distance between these two t's, the system will rephase, and the photon will be re-emitted in the forward direction. And this is basically a collective re-emission in the forward mode, and it's very reminiscent to a photon echo. And the reason why we like this protocol is that now if you come not with a single temporal mode, but with a train of temporal modes, a train of single photons, for example, you will have at the outputs also exactly the same train of single photons. So this is a naturally temporally multimode quantum memory. You can see an example here. This is an example from the lab of in green. You have the atomic frequency come. So this is the absorption as a function of frequency. And you would have this dashed line would be, for example, the photon that you want to absorb. This would be typically for a storage time of 2 microseconds in that case. So you have 500 kilohertz between the peaks. So now this was up to now. This was basically a kind of delay. So the photon is absorbed in the quantum memory and is re-emitted after a predetermined storage time. Now, while the photon is stored in the quantum memory, you can also bring it down with a laser to the spin state. So you change this collective optical excitation for a collective spin excitation. And while they are in the spin state now, you can leave them for a while, and then you can read them out on demand by sending in another control pulse to bring the excitation back to excited states, and then the photon will be re-emitted here. So the spin wave storage allows you to have now on-demand readouts, which means that you can read out when you want the photon, and also to have longer storage times, because now you can take advantage of the storage times in the spin states, basically.
Hugues, can I ask you a question?
Yes.
This is very, very interesting. Thank you. So if I understand correctly, you also mentioned that this can be used for storing different photons when you send the train of photons separated in time, right?
Yes.
And then of course you can distinguish them because they come out of different times too, right?
Exactly.
I see. But while they're stored, like, you know, the ensemble of atoms is in a superposition of lots of different states that you cannot distinguish. You can only distinguish them when they come out, right? Because time is the only tool that you have for distinguishing them. Am I getting it right? Or would there be a way to play with them, process them, distinguish them while they are in the memory, or that's science fiction?
So indeed, time is the only way that we have to distinguish them outside, at least when they emit photons. But all these excitations have different phases. So in principle, you might imagine that if you were able somehow to measure this phase in a way, you could perhaps do something. I see. But indeed, it's not so easy to process them while they're working in the crystal. So usually what we do is to read them out and to create photons at different time.
Great, fantastic. Thank you. That's really cool. Thanks.
Okay, so now we have shown how the memory works. So let's see how the source works. So we need also a source of entanglements if we want to generate then this entanglement between two crystals. And so our source is a spontaneous parametric down conversion source, and it's non-degenerate in the sense that one of the photon will be resonant with the quantum memory at 606 nanometer, and the other photon will be at telecom wavelength. In our case, for technical reasons, we use 1436 nanometer. And the source now, so down conversion, typically, if you have a source with down conversion, you generate extremely broadband photons. And so this would not be compatible with the quantum memory. So to make it compatible with the quantum memory, we insert this crystal into an optical cavity. And this cavity has two nice things. First of all, it filters the mode such that we have ultra narrowband photons at the output, so around 2 megahertz. And it also enhances the emission in this cavity mode. So we have the pair creation probability within the cavity mode is enhanced by a factor which is proportional to the finesse square in that case. And so basically you can also, it's not only a passive filtering, but you also enhance the creation in this particular mode that you want. And so if you look a little bit more into what state we create with this source, so if you are in a cavity, you have always many longitudinal modes. But now, since we have two very different wavelengths, the free spectral range will be slightly different for these two wavelengths. And so at the end, what you will create, you will have only a few modes which will be doubly resonant. And so you will create a state with typically 10 to 15 spectral mode in these photonic states. And what we will do for most of the experiments that I will present, except one, is to put a spectral filter to select only one of this spectral. And so this spectral filter will now basically get rid of all the other modes, and we keep only one. And this mode again has a bandwidth below 2 MHz, so in principle it's compatible with our quantum work.
Is there a reason? I'm sorry, I will also. Hi, this is René. Is there a reason why you use a bow tie cavity, or could you also use a linear cavity?
Yeah, that's a good question. This is something that we tried at the beginning. We could also use in principle a linear cavity. One limitation that we need to have a long cavity actually, because we need that our bandwidth is something like 2 MHz. And we have intra-cavity loss because we have a crystal inside, and so we cannot have increased the finesse to
understood.
High.
Okay.
And so we could, in principle, also have a Fabry-Perot cavity, but it was easier, let's say, from practical point of view, to have a bow tie in that case because we need this long cavity.
Okay, and so it has nothing to do with stability or so. That you do some clever mechanical design. It's just practicality that you don't want to have a very long. Yeah,
exactly. In principle, we could have also
okay.
a Fabry-Perot cavity.
Mm-hmm.
So yeah, you're welcome. So this typical experiment that we do with to test this cavity. So we have this cavity, we generate these photon pairs. We separate the two photons. The idler photon is a telecom again, and the signal a 606. And one thing we do is to, for example, to detect the idler photon, and this will project now the photon at 606 into a single photon. And we can then do a heralded autocorrelation. We can send this photon onto a beam splitter and do a heralded autocorrelation, and this is the result. So we can see that the function of the pump power, the heralded autocorrelation increases, and this is typical from a dot conversion source. That let's say the quality of your photon is inversely proportional to the pump power that you use. Then we can also put now our crystal where we store light with an atomic frequency comb, and we measure, for example, the cross correlation between this photon at telecom and now these photons stored and retrieved from the quantum memory, again as a function of pump power. And this is so the cross correlation is the probability to have a pair of photon divided by the probability to have a signal and an idler photon. And again, this is typical from the conversion system. You have a cross correlation function that increases as 1 over decreases as 1 over the pump power. But for all the values that are above 2, we are dealing with non-classical correlation. So you have this thin line here, dash line, which is a 2, and this is the limit of let's say the classical correlation, non-classical correlation. So we are already deeply in the non-classical correlation in that case. So this was now storage in excited state, but we also have done experiment where we have stored light now in spin states. So again, you have here an example of storage in excited state. We have again this photon pair source. We detect the telecom photon, and we create now a single photon into this mode that we will store in the memory. And now you can use these control pulses that I told you before to convert the excitation, the optical excitation, into a spin excitation. And what you see here on the right will now be what we call a spin wave echo. which is a photon which has been absorbed by these atoms, sent as a spin excitation for some time, and then read out. We also showed that we can have non-classical correlation now between this collective spin excitation and the telecom photon, and we have this quantum correlation, and in principle now we could store it for ultra long storage time. At the moment it's not super long. If I come back, we are talking about a few 10-15 microseconds, and this is limited by actually the spin inhomogeneous broadening, but we could use spin echo sequences to in principle go much longer. This is something that we are working on. And recently we have also extended this experiment now to entanglement, where we're able now to store entanglements also in this spin state, light matter entanglement.
Hughes, one question.
Yeah.
One question. So when the state is stored in the spin states, and so you still have this process of dephasing and rephasing all the time, right? So you have that oscillation going on, right?
So when we store in the spin state, the optical dephasing is frozen in that case, because we have nothing is in the excited state anymore. But we still, however, have.
I see. So you're saying that there's no Hamiltonian there when like the Hamiltonian is zero at the level of the spin states, or
yes.
So the phase they had at the optical level is inherited and stays there, and then you recover that, right?
Exactly.
Okay.
When you read them out, then you resume the phase evolution, and then you will emit the photon when the atoms are in phase.
But then is it correct to think that the spin Hamiltonian is negligible, or am I thinking it right, or like?
No, because, well, actually, this is the first approximation, but then in the spin state, actually, you also have inhomogeneous broadening, so you also have some phase evolution, and you have also dephasing in the spin, so you have the coherence in the spins. But to first approximation, you also have this inhomogeneous broadening, so you have another dephasing, inhomogeneous dephasing, if you want, which comes, but it's much.
I see. Slower, exactly. I see. Okay, great. Okay, thank you. Thanks. Great.
Can I also ask something just along this line? So why is it so? As you explained how your atomic frequency comb works, the initial dephasing you get because of inhomogeneous broadening, because your emitters are inhomogeneously kind of sitting in the lattice. Is this correct? Is this the key?
Yes, exactly.
Okay, and then you had this trick, and maybe I missed it, but how do you do this? I mean, how do you shape your it was in this case, I think, the excited electronic state, right? How do you shape it such that it has this comp-like structure?
Yeah, maybe let me come back to So, for example, what you could do, there are many ways to do that, but this is done usually by optical pumping. So one very simple way to do that would be that you take a laser and you remove all the atoms at one particular frequency here, and you can do that. Remember that you can do that because
okay.
Because the homogeneous line of the atoms is much smaller than the
yes, okay. Okay,
so you can really do this kind of what you call spectral hole burning to remove a given population at a given frequency.
Okay, and now what you're talking about is not anymore in the electronic level, but we're now talking about the 2G and S state, right? The two ground states, the spin states.
Yes, exactly. There we don't have this atomic frequency comb structure.
Yes,
so
but you still have like inhomogeneous broadening, right? Because you still have the same problem. Or why is this problem now gone suddenly?
No, this problem is not gone. Actually, this problem is not gone and it's still there. And but the inhomogeneous broadening between the two spin states is much smaller than between the ground and excited state. So we typically between the two spin states we have I don't know, maybe something like 20 kilohertz of inhomogeneous broadening, while in the ground to excited transition is something like 10 gigahertz. So it's really much smaller.
Do we have some intuition? Why is this like this? Why is it much smaller?
So this is we are dealing now with basically a nuclear spin which are much less prone to have to interaction with the lattice, if you want. And so the effect of the homogeneous broadening is much smaller with nuclear spins.
Okay, okay.
Okay, let me just come back to where I was. Okay, so now we have basically shown that we can have this quantum memory, we have this source. So now we would like to basically try to create entanglement between two crystals. And so this is what we have done. This was recently published in Nature. And the idea is the following. So again, we have the photon per source, we have the quantum memory. The meaning of these two stars here is one laser. This is the blue is the pump laser, and the red is the laser that we use to stabilize, to frequency stabilize this cavity, for example. Now we would like to double the system. We want to create entanglement between two different quantum memories. So we have two nodes, and in each node we have one source and one memory. And this actually in the lab, they were separated. They were in two different labs, these two memories, and they were separated by 10 meters of physical distance. But with all the fibers that we had something like 75 meters of fiber. So the first thing to do is to generate now a pair of photon in these two memory. And when we take the idler photon and we combine it into this beam splitter here in the middle. And now when we have this click, again, the beam splitter will erase information about the origin of the photon. So we will generate a state where we have one photon stored in this quantum memory here on the left and 0 on the right. And the other way around, 0 on the left and 1 on the right. And again, here I remind you that there is this phase, which needs to be controlled because this phase is the phase acquired by the photons from the source to the beam splitter here in the middle. And to control this phase, then we use a fiber stretcher. So this is a big interferometer if you want. So we use a fiber stretcher to control this phase. So one very important question is how do you verify that you have entanglement? How do you show that there is entanglement? So we use a technique which was proposed by Steven van Enck in 2005. And the idea is the following. So the idea is to make a quantum tomography experiment. So this is, by the way, as a side remark, so this is a 1001 experiment. So it's not easy to make, for example, a Bell test with this kind directly of states. Actually, we don't know very well how to make directly a Bell test with this kind of states. So that's why we use this tomography technique. And the idea is to measure then the density matrix, and the P's that you have here are the probability to have conditional probability to have A, and J excitations in the memory A and B. For example, P00 is conditioned on a click at the center to have 0 photon in A and 0 photon in B. 01 is to have 0 photon in A, 1 in B, and so on. And 11 is to have 1 photon in A and 1 in B. And then we also want to measure this coherence, D here, which will measure the coherence proposition now between these two states. And typically for this, we will make an interference fringe, and the coherence is given by V times P10, P01 divided by 2. And then if we have this density matrix, we can calculate a concurrence. And if this concurrence is higher than 0, then you can show that you have entanglement in your system. So the conditions experimentally to really reach entanglement is, first of all, you want to have a coherent superposition. So you want to have ideally a visibility of this interference, which is close to 1. And you want to be in the single excitation regime. So you want that this quantity that we call the single photon purity, in that case, P11 divided by P10, P01 is much smaller than 1. So when you have a click here in the center, you want that there is at most 1 excitation stored in the two memories. So how do we measure that in practice? So the diagonal elements, we just put single photon counters at the output of the two memories, and we can measure the statistics. And for the coherence, we recombine the two modes, the output of the quantum memory, into another big interferometer. where we have another then fiber stretcher to control the phase, and then we can measure an interference fringe. So let's first start by measuring the single photon purity. In our case, we've conditioned again on heralding. We have a purity of 0.04 more or less, which means that only 4% of the time we have two photons present, or the other one we have only one photon present, or zero. And then we can do this coherent superposition, and we see that we have now a visibility of 84%, which is not 100%, but it's already quite high. And this is for a 2 microsecond entanglement storage. And if we put that now into our density matrix, we see that we have a concurrence which is higher than zero, not much, but definitely higher than zero. And the reason why actually the concurrence is so small is because we have a lot of loss in our system. So the loss will affect the concurrence. So if we lose, for example, photons between our memory and our detection, we will lose photon. And so for that, we will lose concurrence. So for that, we can correct for this loss. If we want to, let's say, backpropagate the results in the crystal, we divide by the transmission. And in that case, we have a slightly larger concurrence of about 10 to minus 1, let's say, in the crystals themselves. I emphasize here that to the rest, maybe before that, to the rest, why it's not 100% is now because we also lose photons from the source to the quantum memory, for example, and because we have a non-perfect efficiency in our quantum memory. But I emphasize that this vacuum term here now, for if we want to do a quantum repeater architecture, at the end it will affect the rate, but will not affect the fidelity of your measurement, because you will somehow purify it by doing post-selection in your repeater architecture. And so we can, to take this effect into account, we can calculate an effective fidelity without this vacuum component, and we would have a fidelity of around 92%. So this shows that condition on this detection at the center, we have now a collective excitation which is shared between these two different crystals, which are 10 meters apart in two different laboratories. Something actually also important here is the heralding rates that we have. This is something interesting for this kind of single photon or Fock state entanglement, is that the rates are usually high because you need to only generate one photon, you need to transmit only one photon, and you need to detect only one photon. So the rates at the end is quite high. Actually, it's much larger than similar experiment that have been done, for example, with cold atoms. We have a heralding rate of around 1.4 kilohertz. And in fact, these rates could even be higher. So this is now a simulation of the concurrence versus heralding rate using our performances for the source and for the link. And our experiment is here. And if we were now to increase the pump power of the experiment, of the lasers, in our case, we were limited in pump power, but if we buy new lasers and increase the pump power, we could really increase the heralding rates of entanglement up to 27 kilohertz according to the simulation, which means that we would have an average time between two successful events of around 37 microseconds.
And would this be a good idea looking at this? Because is the concurrence, it's not a direct measure, it's somehow an indirect measure of entanglement, right? But I guess if it goes down, it's bad, right?
If it goes down, at the end, if it goes down, it's bad. But again, a lot of this concurrence, the fact that it's low, this concurrence, is due to the fact that we have this loss in the system, which in the end, in the final DLCZ experiment, are sort of purified by the post-selection. So okay, you could still preserve entanglement. So the idea of this graph is that to show that we have always this trade-off actually with probabilistic sources between quality of entanglement and efficiency somehow. Mm-hmm. But we could still have a margin to improve, let's say, at least the rate of entanglement. Of course, this comes at the expense of having lower quality.
And so practically, I think maybe I don't know too little about how this practically works, but I imagine it like this: if my concurrence now goes down, then I have to do more purification in the end, which means effectively I cannot use all my photons which are coming, right? So in the end, I reduce my rate again, right? And so I guess there should be now a kind of a combined figure of merit, which tells me which pump power should I use that I'm optimal in this combined figure of merit, which takes into account this concurrence reduction and the higher heralded rate. Or is this a wrong thinking?
No, that's a very good remark. Actually, this depends a lot on the final experiment that you want to do. For example, if you want to do a multi-link quantum repeater, indeed you will be very sensitive to this. So the error will increase with the number of links, and you will not be able to start, let's say, here at the maximum heralding rate. But if you limit, for example, your number of links, then you could increase the heralding rates without losing too much at the end.
Oh, interesting.
At the end, the figure of merits is indeed the final fidelity that you have for your total quantum repeater, and this required final fidelity will depend on your application. If you want to do QKD or if you want to do blind quantum computing, you have different threshold fidelity if you want.
Super, thanks.
Yes, René, why do you say that the concurrent is not a measure? So in what sense?
No, I thought it's like, as said, I mean, I know, or I once read a paper from reading that we discussed this recently. He also uses some similar, okay, I didn't understand how exactly this works, okay, because I didn't go through the theory paper, but somehow it seems the concurrence tells you if the thing is entangled, right, your system, but it's not, for me, I don't know what it now means. How I would quantify the entanglement just by looking at the concurrence. I think it also depends on how you define your concurrence. But as said, I know too little about it, but maybe Hugues could comment on this.
Concurrence is a measurement. I think you may
I think, okay,
negativity is what you said.
I think in my head it's like this, right? In the ideal case, you would like to measure the density matrix, right? Do a full state tomography, then you know exactly what's going on. But I think this is not done here, right? You somehow boil it down to this one quantity, which then tells you something about entanglement. But maybe I'm wrong. Yeah, I don't know.
No, concurrence gives you the tomography of two qubits. Of two qubit states. So it's not the full density matrix, but it's the full reduced density matrix.
So let's let Hugues continue, please, guys. Okay.
Yeah. Sorry.
The concurrence. Yeah. The concurrence is interesting, but these sort of things are more interesting.
You tell me later, Luigi. I think you know this. I can learn it from you.
Thanks. You, guys. Okay. Yeah. Thank you.
Yeah.
So yeah, just to comment, actually, yeah, we don't measure the full density matrix. There are a lot of elements here that we don't measure, and also for that reason. But all these elements are off diagonal, so this would only increase the entanglement. So the concurrent in that case is a lower bound of the entanglement that we have here. So what we know is that if the concurrence is non-zero, we have entanglement in the system, but it could be that even if with this particular measure it's zero, then we have another type of measure that would show entanglement. So it's not necessarily the best witness for the entanglement in that case. Anyway, so yeah, another important thing, of course, if you want to generate now entanglement, if you want to, let's think that you want to create now entanglement over longer distances, is that you want that your storage time in the crystal is also long. So we have increased the storage time in the crystal up to 25 microseconds. In that case, since it's still storage in the excited state, by the way, and we have seen that then the concurrence is going down with storage time, but it's still non-zero. So we still have entanglement after 25 microseconds. So this, in principle, would allow to have separation between 5 kilometers between the nodes. We have not shown that yet, but in principle, we have the storage time is long enough have 5 kilometers of separation between the nodes. And to have much longer storage time, then we would need to go to the spin wave storage that I mentioned before, which is something that we have not yet combined with this entanglement measurement. And now, a last thing for that experiment, which
Hugues,
also
Hugues,
yes,
just
yes.
Can you make it in 10 more minutes, more or less?
Yes, I will cut maybe the last part of the talk. Or maybe let me cut this.
All right. Okay.
I'll try.
Yeah, you. Let's see. No problem. We're flexible too. Okay, thanks.
A last thing important about this experiment is the fact that the memories are multimode, as I mentioned, and this we have shown that we can store up to 62 temporal modes in that case. But in the interest of time, I will just move now to the last part of the talk, which is what are the next steps. One of the next steps, which could be interesting, is we would like at some point, to go out of the lab and to really make this kind of quantum repeater links a reality. And so something that could help is to really have a fiber integrated quantum memory, not directly, not only solid state, but directly fiber integrated. And what would be interesting for that is, for example, that you could integrate several quantum memories on a single substrate. And you could have an array of quantum memory in a single crystal. And you could interface it, for example, also with more complex optical circuits, including, for example, beam splitters or including detectors and so on. And also, ideally, you would be able to, if you have this integrated waveguide quantum memory, you would be able to really have directly this fiber connection, this fiber detailing. Also, in terms of mechanical stability, it's very good. And if you have waveguides, you confine more the light, and so you have an enhancement of light-matter interaction. So these people have shown integrated quantum memory, waveguide quantum memories in the past. This was done directly, for example, doping known waveguides with rare earth ions. For example, lithium niobate waveguides have been doped with rare earth ions, or erbium doped fibers also have been used to generate some quantum memories. But recently, there are also another possibilities, which is to fabricate waveguide in the crystal that we use for the quantum memory. So this first technique here of doping directly the waveguides usually lead to quite low performances in terms of storage time, because the material is not optimal for doing quantum memories. So now people are trying also to generate waveguides in the crystal that we want to use for this quantum memory. And we have proposed a few years ago to use femtosecond laser micromachining to create now waveguide into these crystals. And this is some experiment that we do in collaboration with the group of Roberto Zelame in Milan. And they do the fabrication of the crystal. And so the idea is simple, is to shine a femtosecond laser on the crystal, and this will generate a region where you have a slightly higher refractive index, and this will guide the light in the. So it's a very nice technique because it's direct, it's cost effective, and it's very fast, and it has a nice property also that you can in principle have 3D fabrication. So you can imagine that you have an array not only of waveguide at the surface, but also in the depth of the crystal. So you could really have a lot of these waveguides. And so a couple of years ago, we have shown that we can store single photons in these waveguides. I will go fast to this. And also that we can use these waveguides to make a frequency multiplexed quantum memory. So the idea there is that maybe you remember in when I presented the source that we have this kind of spectrum with 15 modes out of a photon pair source. And what we were doing is to use this filter to select only a single mode for all the experiments that I've shown up to now. But in fact, we don't have to do that. So we can also try to remove this filter. But now, of course, all of this state there will be lost unless in our quantum memory, so this is now the absorption in the quantum memory, we are also able to burn multiple AFCs at different frequencies, multiple atomic frequency counts at different frequencies. And this is something we can also do. So now we can take advantage of the spectral multiplexing in the inhomogeneous broadening of the crystal. And then we do always the same experiment. We have our source, we herald, we detect a single photon at telecom, and we store the single photon now in the memory. And this is what happens now. In red here is the spectrum directly only of the source, and in orange is the spectrum of the stored and retrieved light. So this is now the function of frequency. And this is for single mode memory where you have only one AFC burn. This is what you see. But now when you have many atomic frequency burn at different frequency, we can see that we can store actually the full spectrum of our single photons. And so we stored up to 15 frequency modes. These combine actually to 9 temporal modes with the naturally stored with the AFC. So in total, we had 135 modes now stored in this crystal. But now this was, so far it was an integrated quantum memory, but it was not fully integrated in the sense that we were addressing this quantum memory with bulk optics. We were focusing the light with bulk optics into the wave. What would be nice is directly to connect now optical fibers and to really glue optical fibers to the setup to have a fully integrated setup. And this is what we have done. So Giacomo Corielli from Milan has done this. We have really glued now this optical fiber to this crystal. And so we can have now in principle a fully integrated quantum memory. We don't need any bulk optics from, let's say, to couple into the memory. So this will be again the setup now. We're the same. We have telecom photon that we detect. The signal is now coupled into a fiber and directly to the memory, and combined now with a 9010 beam splitter with the light that we use to prepare the AFC. And we have an end-to-end transmission of around 25% in that case. And we show that we are also able now to store single photons. This is now the efficiency, the function of storage time. And actually, if we compare to result that we had previously with the same crystal, but without the fiber coupling, we see that we are actually even better in that case. And this is because this situation where we have now the fiber coupled memory allows us to have more freedom to damp the vibrations due to the cryostats. I will skip that. And finally, we have also shown that we can now store light matter entanglement into this crystal. So we have again our source. And now we will generate energy time entanglement with our photon pair. And the idler is analyzed with a fiber interferometer. The signal is stored in the quantum memory and then analyzed again with the fiber interferometer. And we are able with this, so it's what we call the Franzen setup. We are able to post-select the states where the two photons pass either to the short arm of the interferometer or to the long arm of the interferometer. So we have a kind of early plus late states that we can post-select. And with this, we do a tomography as well. And with this tomography, we are able to show that we are able to store the entanglement. This first one here is just with a transparency window, and we have a 2-qubit fidelity of 75%. This is without quantum memory in that case. When we correct for the analyzers and for the imperfections, we have something like 80%. But now, if we put the quantum memory, we can see actually that we have an increased fidelity, which goes up to 86% with 3 microsecond storage, and also 86 with 10 microsecond storage. And the reason why it's increased fidelity with the quantum memory, that the memory serves as a filter, both in frequency and in time, to remove the noise that you have from the source. And this is something that we have observed also in the past, that when you have the memory, you have higher fidelities for the storage. And so this shows that we have entanglement, and actually this entanglement in fiber integrated systems is 3 orders of magnitude, the storage time is 3 orders of magnitude higher than what has been shown before. And the efficiency is also an order of magnitude higher. Okay, and this I mentioned before, we could also extend this now to spin wave, as we showed with bulk crystals. But in the waveguide, it's a little bit more tricky to do that, because you have still a lot of noise. But we are working on this. And finally, this will be my last slide before I conclude. If we dream a little bit in the future, so we saw that multimodality is a key ingredient if you want to build quantum repeaters, because it really boosts the entanglement rate, let's say this to total number of nodes. So we could try to combine different type of multiplexing. So for example, 20 temporal modes is something we have shown. 20 frequency modes, we are not so far away. And maybe if we could build this waveguide arrays together with this fiber pigtailing that I have just demonstrated, we could imagine to have an array of 10 by 10 waveguides in the crystal. It's not completely crazy. In total, this would give already a total of 40,000 modes that we could store in this crystal. So this really, if we're able to harness all these modes, and this, of course, there would be a lot of technology involved to harness all of these modes, but in principle, we could really boost the entanglement rate by a big factor. And this could be a game changer in the future. Okay, so let me now conclude. So I showed you that we have demonstrated entanglement between 2 remote solid-state quantum memories heralded by a telecom photon. It was done with multimode memories, which potentially are massively multimode memories, and it's compatible also with telecom networks. So in principle, this experiment is extendable to long distances. We have shown that there is a potential for fiber integration, and of course, now we need to improve performances in terms of storage time, in terms of efficiency, in terms of number of modes, if we really want to go a step forward and to go to large scale network. So this is actually something that we are really interested to do, to really try to build a quantum repeater, to really go out of the lab and make demonstrations of quantum repeater. So we need to increase the distance first. That's the first thing to do. Go to spin wave to increase the storage time. And then we need to double the setup, because this number state entanglement is nice for generating entanglement, but it's not so well suited for doing QKD, for example. So what DLCC proposed is to have 2 chains of quantum memory, entangled quantum memories like this. This is something we are working on. And then we want to scale up and build, do entanglement swapping between 2 repeater links, and try to build a repeater that would beat, let's say, the direct transmission of quantum information. Okay, let me, to finish, thanks a lot my group, sorry. So this is actually a very old picture, pre-COVID, but the people in red here are still in the group, and they are the one who contributed mostly to the experiment that I have shown you in this talk, and together with Margarita Mazzera as well. And yeah, we do have open PhD in postdoc positions if you are available. If you are interested, just contact. So with this, I thank you for your attention.
Thank you so much, Hugues, for such a fantastic talk. Amazing work that you guys are doing. This is really, really cool, really interesting science. There have been some questions, but we have time for 1 or 2 questions. And in fact, I do have a question. So I take the privilege of asking the first question, okay? So, okay, this is amazing. The final outlook that you showed, the possibility of storing up to, I don't know, 40,000 modes where you can store 40,000 qubits, if I understand correctly, if one thinks of quantum information. Now, So I wanted to hear your opinion on what's like the killer application, because I understand that there's no way to process quantum information inside the crystal, right? You have to read it out, you have to encode it back into light to be able to do something, right? So what's I mean, what's the goal of having so many qubits or quantum information stored into the crystal if you cannot process it? Just store it. I mean, like I wanted to hear if like what would be like the first application. You mentioned something about blind quantum computing. Perhaps you would like to create some stabilizer state inside of the like if you're allowed to dream about the future, like what's the idea of having so many qubits stored in a single crystal?
So well, the first idea is that it would really help the scaling, just because you have this multimodality, so you can per communication time you will be able to store to try, let's say, 40,000 times instead of trying only one time. So you would increase, let's say, the rate of entanglement or at a distance. So basically, every time for each communication time, you would create deterministic entanglement.
I see.
Or at a distance. So I would say the first application is really in this quantum repeater.
Quantum repeaters, right? With high repetition rates, right? That's
with high repetition rates.
I see. Right.
But then once you have generated this entanglement, it's true that right now we cannot, with ensembles, we cannot. At least I don't know how to do really processing now between these different qubits. At least not between two different qubits, or two or more. But then you could imagine to transfer this entanglement. Once you generate it very fast, you can transfer it to other type of nodes that could do that. And actually, I haven't mentioned that, but rare earth ions, if you're able to detect a single rare earth ions, you could in principle also have some strong interaction between ions and have a way to make quantum gates between different ions. But for this, you need to be able to address a single ion, which is something that we're also working on.
Okay, fantastic, thanks. René, is there something else that you would like to ask?
Yeah.
Thank you.
Sorry for hijacking.
No. Thanks.
Yeah, it's a very practical question. So we are in our lab here, in one of our labs, we do some levitation of particles, and I also tried once to levitate an erbium doped particle, like optically. You use a tweezer, you put it in the tweezer. You might know, of course, you know Roman Kidon, right, at ICFO, he's doing this.
Yes.
Or Lucas Novotny he's my former boss. And so, and the thing was, it didn't work because the optical absorption, that's the guess of this little nanoparticle, we used nanoparticles back then, was just too high. And so I was wondering now, can you tell me anything about kind of the cleanliness of your crystal and also maybe the optical absorption? So let's say I would get one of your crystals and I grind it down and make nanoparticles out of it, and then I try to levitate it. What are the chances that the absorption is so low, similarly as glass, that I can levitate it in vacuum and do something with it in ultra high vacuum?
That's a good question. I think so. People, for example, have tried to make whispering gallery mode cavities with these crystals. There is some experiments that have been done in Jevon Longdale's group, I think in New Zealand. And I don't have in mind now exactly what is the loss inside, but they could have reasonably high Q with their cavity, which would tell me that the loss in the WISO crystal is actually quite low. And I don't know now if this could translate directly to this kind of application, but it's some. So if you look in the paper of Jevon Longdale, he had a couple of papers, I think, where they measure that.
What's his name? Jevon
Longdale.
Jevon Longdale. Okay.
If you, I can.
I will type it here in the chat. Maybe. Yeah. Fantastic. Longdale news. Okay, and then very practical question. So are these crystals hard to get by, or can I just buy them somewhere?
We buy them. We buy them at Scientific Materials, a company in the US. Yeah, they are more and more expensive, but still reasonable.
Okay, super. Fantastic. Thanks.
Excellent. Thank you, René, for the questions. Is there anything else that somebody would like to ask to Hugues to take advantage of this last minute that we have him here.
I mean, I have one more, if I may, but of course I don't want to.
No, go, shoot.
No, but maybe if somebody else wants to say something.
I think that nobody seems to react, okay, so please go ahead.
I had a question at the very beginning as you talked about the applications, and you said you could use it to improve telescope arrays and for clock synchronization. I don't get where's the quantum part coming in here if I wanna look at a telescope array or a telescope which is measuring quantum information.
Right. So there is this proposal by I don't remember whom now, Riedmatten, for example, to basically. So the idea is that to link two telescopes, right? So if you have a telescope array, then it's like having a much bigger telescope in terms of the sensitivity, but let's say so the idea of this proposal would be to put a quantum repeater between the two telescopes to share an entangled state between these two telescopes, and then to combine the photon coming from the stars together with this entangled state. And this would allow you basically to have like a phase stabilized, because you need a phase stabilization between the two telescopes in principle. And if you have single photons coming just from the stars, it's not something quite easy to do.
Interesting.
And so it's a bit science fiction, this paper. I mean, the performance that we need for the repeater are much beyond what we can do at the moment. But I found that it was an interesting application because it's something completely different than what we are used to.